Next, we want to compare a few different kinds of motion. Translation, which is what we've done up until this point, is when the center of mass of an object is moving. Spinning, on the other hand, is when the center of mass stays put and the rest of the object rotates around it. If we look here at this figure, we see that the velocity of every point on the wheel is the same if you're sliding. This is pure translation. On the other hand, for spinning, pure rotation, the highest velocities are at the extreme edges of the wheel, and they would be v forward or minus v backward at the bottom. If I add those two things together, those two kinds of motion, I get rolling without slipping, which is what your car tire should be doing normally. That means the top part of the tire is going twice as fast as your speedometer says. V is going, the center of the tire is going at the speed your speedometer says, and the point of contact between the tire and the road is actually not moving at all. And that seems kind of hard to believe, but you can do this experiment if you tape a piece of newspaper or tissue paper or something across the driveway. If you went sliding across it with your brakes locked, you may have to try this with a bike since most cars have anti-lock brakes now, you would shred the paper. On the other hand, if you were parked on the paper and you floorboarded it so that you spun the wheels, you would also shred the paper that way. If you went driving across it normally, though, rolling without slipping, you wouldn't damage the paper, and that's because there's no motion between that part of the tire and the paper. The way to express this mathematically is to say that x equals r theta, or v equals r omega, or a equals r alpha. Those all mean rolling without slipping. If we use this and kinetic energy of rotation, we can solve some new problems. Let's say we have a disk, and we know its moment of inertia is 1/2 mr squared, and it's at the top of a hill of height h. It doesn't really matter what the shape of the hill is. This is one of the benefits of the energy method. It's going to roll down the hill, and we want to know how fast it's going at the bottom. At the top, we have nothing but gravitational potential energy, which is mgh. At the bottom, we're out of potential energy, but we have two kinds of kinetic energy. There's 1/2 I omega squared, because it's rolling, and 1/2 mv squared, because it's also translating. Conservation of energy means that those two things have to be the same. If we look at this, we could plug in the I. Keep in mind that I for a disk brings in its own factor of 1/2, so we have two factors of 1/2 in that term. And we can rewrite the whole thing like this. We can cancel the masses and get this. Here we have two unknowns. We don't know omega and we don't know v. Since we only have one equation, we have to find another one. And we get that other equation by realizing what rolling without slipping means. When we put in v equals r omega, we can rewrite this whole process, gh equals 3/4 v squared, or v is square root of 4gh over 3. If instead of a disk we used a hoop, we'd have I equals mr squared, and the only difference would be when we did our math and got all the way through it, we'd find we get v equals square root of gh. So what this means is if you have a hoop and a disk in a fair race down a hill, the disk will win. The hoop spends more of its potential energy rotating than it does moving forward. If we then move on to the rotational equivalent of Newton's second law, we have, which is sum of the external forces is ma. We'll use that form for right now. That's useful, and what we'll do is we'll replace m with I, like you would expect, and a with alpha. The rotational version of force is torque, and if we have a force that tends to cause a rotation, that will create a torque. So we can define a torque as the cross product of r and f. So we could write that as magnitude of r, magnitude of f, sine theta, where theta is the angle between r and f. R is the distance from the center of rotation to the point where the force is applied, and the fact that it's a cross product means that the torque vector is perpendicular to both r and f. The direction of torque is found by pointing the fingers of your right hand in the direction of r and curling them in the direction of f. After that, your thumb will point in